these beautiful devices, all these, and you may not like it. They don't like it. Now, radiation, nuclear radiation, right? But I want you to know that while I've been telling you this sentence has been hit, the good news is it probably touches nothing. Is some of the particles you can, some take many minutes. So, give you some of the terms. Be familiar with. Sit down. And I want you to know that in the hour we spend this morning, you're not going to leave an expert. But from device and of this your device now works. In that vein, we can give you some idea of what radiation is. First, now you can't do radiation effects unless you can measure the radiation. You got to know how much of what's doing this to your device. So basically, there are three types of radiation that we want to talk about. Now, a nuclear weapon, which is all about, I talk about them very much. I will as I go through here, but basically we want to talk about gamma radiation and X-ray. Gamma and X-rays are both what we call photons, as opposed to neutrons, which are particles. Actually, photons have a rest mass of 0. It's the way you want it, you catch it in your hand. It's a packet of energy, which if you move it fast enough, interact a bit more about the character of these things. Now, well, the way we do it, primarily its idea is we measure it with a unit that we call a rad. Now, a rad is nothing more than a measure of SOR. It's the energy measure, just like a calorie. See, everybody's familiar with a calorie, because that's what you use to heat water with, calories from your stove. And an erg is not very much of that, but a rad stove. And an erg is not very much of that, but a rad is 100 ergs per gram. And we also hear the term cal, and that's just a whole bunch of rads piled up in the same gram of material. Grays. Now, gray is a unit that they came out with when they tried to standardize, and that's just 100 rads. So you can relate all these to calories or to joules or to ergs because they're all basically the same type of unit. And the unit is the absorption of energy to 1 gram of material. Now, the best example I can give you of what this is all about is sunburn. Everybody's been sunburned, okay? When you get out in the sun and inhale, and the sunshine convert into calories per square meter. Then if you want energy, X-rays, Lincoln is named after the man who discovered, and he made of so many ionizations in a vapor to look at. We're interested in, so we RIM, the health physicists use those. That's a rad equivalent mammal or person. And all that is the energy absorbed in tissue. And what's tissue? It's mostly water. So we're talking about energy absorbed in water. Now, neutrons are an entirely different animal. They are a particle. They're a little bullet coming at you very fast. So we have to measure that in a different way. We have what we call a flux of neutrons. That is, in a certain period of time. It's sort of like putting a screen on your water hose. How many gallons of water are coming through there in a minute? That's your flux. And you measure for 2 minutes and how many gallons you get. That's your fluence, the time integral of flux. And the units that we use there are very descriptive. Neutrons per square centimeter is what we usually see the fluence called it. That means how many of these particles have hit this square centimeter in this period of time. And that's what you're interested in. Sometimes if you get some of the old literature, they will interchange neutrons per square centimeter with NVT. Just want you to be aware of that. NVT is the very same thing. It's neutrons per centimeter squared. The only thing they've done is they've called that out in what it takes to. So don't let it throw you. It means it's a flux factor that's there. So you're going to talk about rads, because that's the energy that it deposits in your device. If you talk about neutrons, you're going to talk about how many of those particles pass through your device, because that's what you want to know. And we're going to find out why. Now, X-rays are a little bit different. X-rays are photons also, just like gammas. They're just a different energy, or a different wavelength, if you like to think in wavelengths. Usually it's the evolution of the history here is the reason we call those calories per square centimeter, which is the flux, or calories per gram, which is the energy absorbed. Because in the early history of nuclear weapons, we knew that there were X-rays coming out, but the manifestation that we saw them in was heat. So we call them calories, because when you think of heat, you think of calories. But it turns out that some of them had a photon energy that was great enough that they act, not like heat, but more like particles or high energy photons that penetrate things. So we really ended up with sort of a misnomer there. But calories per gram can very readily be converted into rads because they're both energy absorbed. Yes, John?
Which has the higher energy, the gamma rays or the X-rays?
The gamma rays are the higher energy photons. Usually we speak talking about photon energies, from 10 keV up to 100 to 150 or 200 even, depending on the materials. Into that a little later. Gamma photon energies we usually think of from a half MeV on up. And that period those energies in between are sort of gray, and we'll refer to them as one or the other depending on. But that's the energy regimes that we're talking about. It does make a difference, and we'll talk about that a little bit when we get into the basic interactions, which we're going to do right now. Now, these basic interactions can get very complex. The interactions that I've got on this view graph, I could turn into a whole semester if I wanted to. But you don't want to do that because there's lots of long equations and things like that that you'd have to know. And I don't want to tell you about that this morning. I want to give you a simple picture of what these interactions are doing to your device. So, we start out with gamma radiation. Photon radiation ionizes things. That's what the photoelectric, the Compton, and the pair production, which are the three possible ones, do. They ionize your devices, whether it be silicon or oxide, silicon dioxide. What they do is they create charge carriers in there. And they create a lot of them. They create whole electron pairs, if that's what you like to think in. So that's what I want you to remember. Now, the photoelectric effect is associated almost entirely with X-rays. Or put another way, X-ray interactions are almost entirely photoelectric down at that energy. Gammas are mostly Compton. Pair production is an interaction that takes place at very high energy photons and cannot happen until you get a little above 1 eV. Usually we're not too concerned with that because what we call the cross-section, or the probability of it interacting with your material, is very small for pair production compared to the other two. So we don't fool with that one much, but we do talk a lot about photoelectric and Compton. Okay, and I'm going to give you a little more picture of this a little later. Now, neutrons, like I said, are a particle. And what they do to you, you're interested mostly in its interaction with silicon. Let me give you an analogy. All of you have shot pool, right? Yeah. Or you've been in the pool room. I know you've been hanging around the pool room when you weren't supposed to. And you all watched them shoot the cue ball into those other balls. Well, a neutron going into a silicon lattice behaves sort of like that. That neutron is smaller, but it's going much, much faster. And it comes in and it hits the silicon atom. And that silicon atom now becomes the 8 ball or the 4 ball that goes rattling around, hits all those other balls, and moves them. That's what it does to your silicon lattice. It knocks them out of place. And that does bad things to you. And we'll find out about that. So really, all I'm going to illustrate this morning is what we call the elastic scatter, or the billiard ball interaction, that knocks the silicon atoms out of place in the crystal. That changes the operational conditions and the behavior of your device. There are others that you might be interested in at some period of time to get into radiation effects, but we'll talk about those later. Now, the reason I've set X-rays out separate here is that photoelectric does a couple of things in X-rays that gammas don't. The absorption coefficients, or the amount of energy that's soaked up in the photoelectric interaction, is much greater than in Compton. So if you will imagine your device sitting here and you put a whole lot of energy into the surface that you're hitting, as opposed to gammas that deposit energy basically uniformly throughout the device, we're going to put all of this in the top 2 microns, let's say. It's going to ionize the fool out of it, but it's going to do something else. It's going to create a shock wave because you've dumped a whole lot of energy into a small layer in a short period of time, and it can't dissipate. You know, the thermal heat expansion, for instance, what's going to happen there? It's going to create a shock wave that propagates through that device, and when it hits a dissimilar boundary, it may break it apart because of the shock wave. But we'll talk about that a little bit more too. So X-rays do one extra thing. They ionize, but they also can induce shock to your device. And so we have to, in radiation effects, be concerned about that also. Now let me give you a little bit better picture of what I'm talking about, starting with the neutrons. Here comes a neutron. Here comes the cue ball. And, you know, it goes through the lattice for quite a ways, but finally it hits something. And what happens? It knocks that atom out of place, and it hits another one. And it knocks it out of place, and it hits another one, or bounces over and hits another one, and you defect cluster. Because before you dissipate all that energy, before all the pool balls come to rest, you've moved several of them. And so you end up with defect clusters in your crystal. Where you had a nice orderly arrangement, now you've got what we call vacancies and interstitials because they're out of place. A vacancy is where one ought to be and is not, and an interstitial is where one is and it ain't supposed to be. So, you moved them around. And as you might imagine, depending on how fast your cue ball is going, depends on how many of those defects you make. So if you've got a 1 MeV neutron, it'll create so many, but a 14 MeV will create about 3 times as many because it rattles more of them around. So the picture I want you to get is this neutron is moving the atoms of your crystal around and it's changing the characteristics. Now let's look at a Compton interaction. Here comes a 1 MeV photon. Now what happens to it? It smacks into an orbital electron in one of the atoms in your oxide. And that electron that it hit goes flying out of orbit. And it does the same thing to others, and finally it uses up all its energy knocking electrons off of atoms. It's ionizing. It's creating free carriers. It's creating free electrons, which are charge carriers in your device. And there's a photon of a lower energy that goes off and usually escapes from your device before it interacts again. But the thing I want you to remember is that it's creating free electrons, electrons that can move when you put a potential on that device. Whether you want them there or not, they're being created by the radiation. Now, both of these things happen, especially the photons, which I'm going to illustrate here. The probability of them hitting something and the amount of energy they're going to deposit varies with the energy of the photon. Now, here's your photoelectric effect, which is very high at low energies. Here's your Compton effect, which is intermediate out here at an intermediate energy, and here comes your pair production in at higher energies. And I just wanted you to see for aluminum or silicon, which is about the same, that these things vary with energy, and you get slightly different types of interactions. But the high energy photons are all going to ionize your device and create charge carriers in there. Now let's illustrate this with a device. You know, the equations are there if you like equations, but what I want you to remember, here's a diode. You've got a p-n junction, you've got a potential here, so you're creating a depletion volume that I'm sure somebody has told you about already. And what happens? These photons going through that volume create just scads of electron hole pairs, and that device thinks, hey, somebody has turned me on. You know, they must have. I've got charge carriers here. How'd they get here if they didn't turn me on? So it acts just like you turned it on. And it puts a big pulse of current that we call photocurrent through that diode, even though it may be turned off in reverse bias to create your depletion volume. It acts just like it's turned on. And zap, a big pulse of current goes right through it. Now,
could the device be burned out because of that?
The device could possibly be burned out depending on how you've got it hooked in a circuit. Very rarely do you see a device destroy itself just sitting there, but usually you never have that. You know, I won't say usually, you never have that because somewhere you have stray capacitance or a bypass capacitor or something sitting there charged, and if you've got that case, when you turn it on, it'll dump right through it also and could very well ruin the junction of your device. Sometimes, in the case of MOS devices, which we're going to get to, you may generate a voltage spike somehow big enough to punch through your oxide too. That's especially a weakness of devices that you're not building, called VMOS devices. When you get in high dose rates, they'll punch through the sidewall. Okay, so you're creating photocurrent, we call it, which is nothing more than radiation-induced free carriers that make that device behave like you don't want it to. And if you've got it sitting in one of John's logic circuits trying to perform a function, when it's supposed to be off, radiation turns it on, it's going to mess up your logic. So high dose rates then just totally wipe out your logic states. It's what we call dose rate upset, and it happens. And it happens to any type of active device that you can put in an ionizing radiation.
If the device is not turned on, if power is not turned on to the device when that happens, Floyd, and you turn it on an hour later, do you still have that damage?
No. This is strictly a transient effect, what we call a transient effect. The ionizing radiation coming in a pulse creates a pulse of photocurrent which for a short period of time upsets your logic, turns your device on, but as soon as your circuit potentials restore themselves and sweep those carriers out, you'll go back to some initial stable state. Maybe not the initial one, but to a stable state of your device. So the upset from dose rate is a transient phenomenon.
This is the gamma radiation. What about the neutrons? Are they entrapped in there and staying there?
The neutrons are not entrapped in there, but the damage which they cause is. And we're going to talk about that in just a minute. I'm getting there if you'll just hang on. Okay. Now the neutrons, you know, I can show you the same type of photocurrent in a planar type of transistor. There you've got two junctions that you create photocurrent at. But you still get photocurrent by the same mechanism. That is, you ionize the device, you generate charge carriers in your critical volumes, and you get photocurrent. It's going to be there, folks. Nothing you can do about it. So what we have to do is learn to live with it. Now, in bipolar technology, well, you know, the neutrons also cause big effects to lifetime, and we have equations for that, but really what I can do is I can put your device in a pulse of radiation of a certain width, and I can look at the photocurrent profile, and I can tell you whether you have a short lifetime device or a long lifetime device. Because the photocurrent profile depending on the pulse width and the lifetime, will either have a very sharp rise and fall, or it will have something that goes tailing on out. What's happening there? The lifetime of your device is long, and it takes a long time for the field to sweep all these carriers you've generated out and restore the device to its initial condition. So, you know, sometimes radiation effects may look a little bit like magic, because I can look at this pulse and say, gee, you've got a long lifetime device here. And you say, well, how do I know that? Well, I know that because of the way it's behaving. The way that it has, you know, these carriers have to behave. Now, the neutrons do several other things to. There's a slight error on this view graph, but I won't point it out. Somebody asked. They do several things. Neutrons, when they create these defects in your crystal lattice, the defects stay there, most of them. You know, some of them do fall back where they belong, some of the silicon atoms because of thermal agitation and that type of thing, but most of the defects stay there. And what do? They change the gain of your transistor. And how do they do that? Because if you remember your transistor profile, when your electrons, in the case of an ENPN for instance, are injected from the emitter into the base region and you try to collect them over at the collector, you've created defects in the base region. Now I'm going to talk about the base because that's one of your primary interest areas. That's one of your critical volumes. Because that's where the minority carriers are trying to move through. And these defects act sort of like lots of holes in a putt-putt game. You know, you're putting your golf ball across the green. Al understands this, he's a golfer. And you want it to go in one cup. You want it to get collected over there, the other side of the base collector junction. But the defects act just like lots of cups out there in the base region. And so lots of the carriers that you're trying to transport across there fall into those holes you've created or into those defects. They act like traps. And so as you decrease the efficiency of transporting these carriers across the base, you also decrease the efficiency of your transistor operation, and the gain goes down. The HFE gain, whatever you call it. So you're just shooting yourself in the foot by creating defects in there that act as traps. And so the lifetime of your carrier going across there is decreased a great deal because it's got lots of traps to fall into. It doesn't live nearly as long, doesn't go nearly as far, however you want to look at that.
Well, Floyd, if you really knew you were going to be in radiation with a device, could you design it in such a way that you'd make that a narrow trip?
Sure. What you do is you make your base region very thin as possible, so they can get across in a hurry, and the density of your defects then is the same throughout the device, but fewer of them are in the base. So you have fewer traps, and the efficiency of your device is still remains pretty high. There are other things you can do too. You can put a lot more donors in there. You can dope it higher so that the traps are offsetting the effects of these donors, and so you have to have more traps to offset the donors. That's another way you can do it. Basically, the different types of devices have to be built differently, so their sensitivity to neutrons is greater or smaller. And I'm going to throw up a few different types here, some of which you've heard of, I know, to show you that depending on how a device has to be built, you have a different neutron tolerance out here. These are all bipolar. Bipolars are affected by neutrons because the device behavior is controlled in the bulk silicon. And silicon is what the neutrons are affecting. Now CMOS, the critical part of the behavior there, takes place in the oxide above the gate. Gammas affect that, and we're going to talk about that in just a minute. But here are some of your bipolar devices, and the different levels at which they are affected. And you will notice that, oh, these fairly hard. You know, the I squared L isn't too hard because it has a lateral device in there, and we won't go into that, but some of you know that, you know, some of them are a little more complex, and you notice that the tolerance on some of the old op amps falls pretty low there. We can't use those in the weapon system. Not quite hard enough. Now, neutrons, on the other hand, have a very small effect on your CMOS devices, because CMOS devices don't have this situation where you have to take a minority carrier through a base region or something like that. They're what we call majority carrier devices. Did anybody talk about that? Good. Okay. You know what I'm talking about then. Here's a cross-section of a CMOS inverter that you guys are going to be building or doing something with. And the area that we're really concerned about is the gate oxide. And I'm going to give you a blown-up version here, but what happens there? Well, the gammas or the X-rays go whizzing through the oxide. They create whole electron pairs. Now, an oxide is different from silicon. Silicon is a semiconductor. It conducts pretty well. The electrons can move through that pretty well, but an oxide is an insulator. It doesn't conduct charge carriers very well at all, as you've been told, I'm sure. And it moves the electrons pretty well, but the holes don't move very well at all. So the thing that happens, if I can blow this up, here you have your metal, you have your oxide, this is your gate, and then you have your silicon substrate, semiconductor, T-well, whatever it happens to be. And along comes a burst of ionizing radiation. And you generate lots of whole electron pairs. Well, immediately, some of them will recombine right there in what we call the parent location, or where they're generated. But there's a bunch that won't. And then, because the mobility of the electrons is much greater in the oxide, they get whipped right on out. But the holes are very, very slow and sluggish. And they stay there and slowly move their way down to the oxide silicon interface there and get trapped. That's bad. We don't like that. Because now we've got a charge in that oxide that we didn't want. And it's setting up its own field, which is either going to aid or oppose the bias that you put on that device, and it's going to make it operate different. And it's going to basically shift the threshold voltage, you know, the voltage that's required to turn this device on and off, or off. It's going to shift that value required. And pretty soon, in the case of an N channel, you've accumulated enough charge along there that you've turned it on, you can't turn it off. And pretty soon in the P channel, you've accumulated a sufficient amount of charge in the oxide that you've turned it off and you can't turn it on with the normal biases. So your CMOS doesn't work anymore. Now neutrons, they haven't done much. They've created defects in the silicon here, but you've got so many donors in that you know, it takes a huge number before you really start affecting the mobility or the transconductance through the channel adequately to really change the operation of the device. But in that poor old oxide, it's got trapped charge in there now, and it doesn't operate the same anymore at all. And if you blow the picture up a little bit, you know, it still looks the same, but basically you end up with trapped holes there in the insulator, and the characteristic of the device has changed. This won't operate quite the same now. Your biases have to be different to make it operate, or you start to leak all the time and use more power, and then you just have a situation that's undesirable for the operation of CMOS.
Floyd, as you did with the base design, could you make that oxide thinner? Would that help?
You can make the oxide thinner. You can also do things to take the trap sites out of the oxide, make it pure, or put in ones that will behave slightly differently, so that the amount of the oxide buildup, charge buildup, is much smaller. That's what we call hardened oxides.
How long does this situation last when you've got that charge?
At room temperature, that situation will last a long, long time. We call that permanent. In the case of the oxide, if you do run that up to a couple hundred degrees C for a while, you will free those trap charges and get them out of the oxide. And you will go back almost to the same condition that you were, except the radiation has done one other thing. It's created what we call interface states. Right there at the boundary of the oxide and the silicon, you've got some peculiar material that sometimes is referred to as SiOX, because it's not quite silicon dioxide. And you've got various type of bonding going on that create interface states that won't quite come out. That can sometimes help you too, because when you look at the threshold voltage on the CMOS that we build here, it goes out to about somewhere near 10 to the 5th before it starts degrading. That is, you build up enough oxide in the charge that you are starting to change your threshold voltage. And then the N channels go down, and when they cross the 0 point, they go into depletion. They're on all the time. But you've got some surface states, we call them, that are sort of coming along and doing the opposite thing. And we've come out with a recipe where they sort of balance out. And you see this dip, but if you've got the recipe right, the surface states come out along and balance out, and that curve turns around and goes back up. Now this is a very complex type of physics here. And I would explain it to you, but I don't understand it too well. Nobody does. That's one of the areas that so-called experts say that we really don't have a good understanding of what's going on. And we have some people here at Sandia now that are working on it. Peter Winokur is one of them, and he's recently acquired by Sandia. One of the experts in the field of radiation effects for a long time, George Messenger, says that that's probably the least understood area in radiation effects right now, and he may be right. But anyhow, this particular phenomenon of surface states is helping us at the moment, so we're not going to fight it too well as long as we can keep the recipe right. So what you end up with is a situation that for P channels, you know, your threshold voltage starts out here, and then it goes more negative as you build up more charge in the oxide. So both of the thresholds go more negative. The N channel it turns on, the P channel it turns off. So basically what you've got then for the two major types of radiation that we worry about at Sandia is neutrons affecting the bipolars by creating defects in the silicon, thereby creating lots of traps for your charge carriers, fight their way across the base, and they fall into these traps, and it decreases the efficiency of your transistor. In your CMOS or any of your MOS, what you've got is the gammas creating charge carriers that get trapped in the oxide and can't get out, thereby generating an internal field in the gate oxide, which counters or adds to the applied bias that you've got on the gate. And this continues to the point that the device won't operate anymore. And so you see, depending on what type of radiation you're trying to harden to, you may pick one technology or another to do the job. You know, this is all part of radiation effects, and when you get to doing hardened circuit design, you will take these things into consideration. But when you get to do hardened systems, you have to take all of these factors into consideration. So one other thing that we have to worry about in X-rays is the fact that you have to make sure that you use the right materials so that the device doesn't fly apart when the X-rays hit you. And in that regard, I'll point out one of the things that's important that we have to consider: the photoelectric effect, the absorption for this interaction goes as about the Z of the material, the atomic number. Did anybody tell you about that? No? Well, it's basically the electron density of the material. It goes about as Z to the 5th power. Compton effect, on the other hand, from gammas, it goes as Z to the 1st power. Okay? Now, what are the high Z materials, as we refer to them? Gold and lead. What are the low Z materials? Aluminum, beryllium, those things. So you see, if you were to build your hardened CMOS with gold metallization, you'd have a problem with X-rays, because it would probably blow it right off of the device when you got it into an X-ray environment. But aluminum, no, it's much more transparent, if you will, to the X-rays. So this is one of the things that you have to take into consideration when you're dealing with hardening the X-rays. You have one other dimension there that you have to consider other than just ionization. Now, the X-rays are going to do the same thing to your gate oxide as the gammas did. But in addition, if you make your gate out of gold, it may blow it apart. So that's why you're using aluminum. Now, we had lots of problems with that one time. So we don't want to do that again. Now let me, in the few minutes that I have left, let me run you through a device that most of you have probably heard about to show you how ionization works. This is a device that I tested down in White Sands on the linear accelerator, which is a pulsed radiation machine. And it's a D flip-flop, you know. And I want to show you, as John did, that all these things are made up of the devices that he talked about and the same building blocks that he talked about. So there it is, the master slave of one of the D flip-flops. And, there's one, a blow up of the same thing. Now, let me show you what I'm putting in: a radiation pulse that's 50 nanoseconds wide. And I'm looking at the outputs, several of them, and you will notice that this is just the point where this D flip-flop is upset. You'll notice that, you know, when the pulse comes along, at every output you get a certain amount of gyration, and usually somebody there has to be the weak sister, and this one over here is the one that changed states first. You notice it went from a high to a low state. It went from like nearly 10 volts down to 0. That's usually the way it goes. Not always, but if the output device is in control there, it's a whole lot easier to turn an off device on than it is to turn an on device off, because something back upstream has to be in charge then. But you see, right there is the place where it changed states. And I don't even remember what the dose rate is here, but 2 times 10 to the 9th rads per second, about 3. Now, somewhere there I was hoping that I had a picture of the photocurrent, but I guess I didn't. Yeah, I did. I can't even read these things. Okay, you'll notice that we're going on up in dose rate as we move down. I'm just looking at one of them. And finally, when we get down here at 10 to the 10th rads, even the low states are changing and going high, because you've saturated those poor old devices. You turn them all on so hard that you don't know how are you going to come back on? So you finally have tipped something in the balance of things. You know, the node capacitance somewhere is just right, so that finally these devices that were low or end up going high. You really don't know how that's going to turn out unless you know all the fine details of the layout of your circuit. Because when you overwhelm everything with charge carriers, it may take something, you know, like 1 picofarad difference in node voltage in node capacitance somewhere may mean that it comes up this way every time after you do that. You never know, but it only takes a small amount of some circuit parameter to determine which way it goes. We see this a lot in memories, for instance. Some of them will upset in a very definite pattern, depending on what dose rate that you're seeing. And usually when you check, you'll find out that when you look at the array on the chip, it's the outside layer that's upsetting first, because the capacitance is different there by just a little bit. But usually there's not much difference in the level that all of them upset.
Where that seems to be kind of a chronological line of full dose as you go down there. Is it typical to find something that will upset at the lower, not upset at one dose a little higher, and then not upset at the next one?
Generally, you don't see that. Usually when they hit upset, they will upset at every dose rate above that too. Now they may end up in a slightly different, they may not always come back to the same state after you upset, but they usually will upset, yes.
You really mentioned total dose, it's really dose rate.
Yeah, this is dose rate that we're looking at, rads per second and not rads. But that's something that I hadn't intended to get into. Upset we refer to as a dose rate problem. But you have to understand that there has to be a certain amount of dose in that pulse also. You know, it can't be zero width, yes. Because you have to have enough dose there to create these carriers that we're talking about also. But the controlling factor there we usually consider to be the rate at which you generate these carriers. Because if you generated them very slowly and the circuit was able to sweep them out like they were leakage, you'd never do anything to the operation of your device. But when you generate them very rapidly and just flood the device with carriers like it's really been turned hard on, then you upset it.
Is
Yes.
there always such a long delay time between the instant they get hit with the radiation pulse, and then it seemed like there was hundreds of nanoseconds there before they finally upset or latched?
No, that's the lead time on my trace. See, the pulse is coming right here.
Oh,
And it's not coming here. I do that so that I can see it. But you know, I've got a lead time here too. See. So no, the radiation pulse is coming right here where you get the abnormal behavior. And so there's not. Now, there is a phenomenon that happens in CMOS that we in radiation effects worry about a lot, but I didn't talk about, and I'll throw that in here, and it's called latch-up. Anybody ever hear of latch-up? Okay, now that's a weird one. I'm gonna go back here and get one of these and show you what I'm talking about. Now, you guys that are building these devices think that you're building nothing but CMOS devices, right? Is that what everybody thinks? Wrong. There are bipolar devices in there, but you don't want them. You just have to take them. They're what we call, you know, they're inherently there. And don't you see a bipolar device? Don't you see an NPN transistor? Sure you do. Look right here. NPN. That's a perfectly good vertical NPN transistor. Do you see any more? Sure. Right here you see a PNP. And if you go draw those out, and that's an exercise for the student, You go draw those out and hook them together, and they look just like the equivalent circuit to an SCR. And guess what? The radiation, when it generates that pulse of photocurrent, turns that sucker on. And it stays on until you turn the power off, or until you burn up the device. And so that's why you build most of your devices on EPI, because with a few little tricks of putting it on EPI and a few other things, you can keep that SCR, which we call parasitic bipolars, because they're not important to the operation of the CMOS circuit. If you can kill those parasitic bipolars, you can keep it from going into latch-up. Now,
Say something about DI.
okay. Now, DI will prevent that, because if you build a DI circuit, you will put this P-well in what we call a tub.
What DI stands for?
That's dielectric. You will build an oxide there, which is a dielectric or something. And that is very effective in destroying that SCR action, because now this lateral PNP here is just not worth a darn as a transistor, because it's got an oxide there in the base region.
It destroys the vertical one also, doesn't it?
Yeah, and it destroys that, and so you can't get that SCR action.
What's the
You-
disadvantage? Why doesn't everything go with DI then?
Tough to build. Tough to build. I mean, some people have trouble building EPI, and so DI is even harder. You get into real tough material problems there. So that's one of the what should we call it, side effects that come into building CMOS that we don't want, but we can't do away with. Now, I've got a bunch of other stuff here that we could have talked about, but my time came out just about right, so I'm going to fill it out with one other thing that we worry about that fits in with what I've told you. In the case of bipolars, we generate all of these defects in the silicon that mess up our bipolars. Now, I did state that at room temperature, some of these defects do anneal out very quickly, in tens of milliseconds, for instance. Now, this is important to weapon application, for instance, because when we get a hit from a pulse of radiation from another weapon, we want to know how quick can we go back into normal operation. Okay, in the case of bipolars, you do get annealing. And by that I mean that immediately after being hit, the damage to your device is worse than it is 3 seconds later. You know, your HFE goes something like that and comes back up. 1 over HFE goes like this. So we have to measure that in radiation effects on these devices. So this is what we call early time or rapid annealing. And there are several things that affect that in the bipolars. You know, how heavy is the current you're pushing through them at the time, whether they're on or off, what the temperature is, and that type of thing. But that is there. And in weapon design, you have to take that into consideration. Because, you know, if you really get hit hard, you don't want to come back up and say, I'm supposed to be operating, and this one says, nope, I'm still too sick. I just can't do it yet. That's a problem. So you have to take that into consideration. Now, in CMOS, you have the same problem. The charge carriers that are trapped in the oxide anneal also, slowly. And here again, you get into this black magic of what's in your oxide and how fast they anneal. How fast can you neutralize this trapped charge or get it out? And we have to measure that also. And that usually is a longer lasting effect than the annealing in the bulk silicon of the defects. Depending on what process is used to grow that oxide, it's minutes. Now, fortunately, the recipe that we're using is the majority of that annealing takes place in a hurry. If it didn't, we would be in big trouble.
What do you call a hurry?
In a hurry, most of the stuff that we've looked at, you're out of depletion in less than a millisecond. You're still going up, but you're out of depletion in less than a millisecond. Now, the recovery continues on for seconds. Now, in most hardened, and to generalize again, in most hardened oxides, the majority of the annealing's taking place in less than a second. In unhardened oxides, I can't, it's all over the map, depending on what they've got in that oxide. It can go on for hours, really. And in some of it, it takes minutes to even get better, more than half out of it. So it jumps around a lot.
If you have an elevated temperature, did you say that would go faster?
It goes faster at an elevated temperature. But when you're talking about time scales of a millisecond or less, you usually can't see much difference in the annealing characteristics.
Well, you talked about gold being a problem on the devices, on the metallization of the devices. Do you worry about that at all, if the package that the device is in is gold?
Yes, we do. We worry about that for several reasons. And here, again, is another one that I didn't tell you about. For instance, you worry about gold if it's layered with something else and the shock that it can generate. You worry about gold if it's on the cover of your package, for instance. Because one of the things that happens, and this we call IEMP, which nobody's talked to you about, I know. But what happens there, I'll give you a picture. Here again, it's an ionization picture. But when these photons go through this layer of gold that's on the bottom of your package, here's the top, here's the layer of gold, and here's your device. When the photons go whizzing through there, they knock a lot of electrons free from their parent atom. We talked about that. That's known as photoelectric or Compton effect. Well, these atoms that are right in the surface of the gold, the electrons that get knocked free are scattered preferentially forward, the same direction that the photons are going. Well, the ones right on the surface, the electrons leave the surface. And they end up going right down onto your device. And a lot of them have enough energy to go right through the gate metallization and into the gate. So you're increasing the dose in your gate oxide. We call this dose enhancement. So, that's another of the things that we have to worry about in radiation effects. But in an hour, I didn't plan to get into that. This type of thing also can generate electromagnetic fields, because when you've got electrons that are moving, you have a current. And when you have a current, you have an electromagnetic field. And that's why we refer to it as internal electromagnetic pulse. So that's a whole another bucket of worms, and my time's up, so I'm not going to get into that any further. But in 1 hour, I just hope to give you a flavor of what oversimplified flavor, admittedly, for what we in radiation effects have to worry about concerning the devices that you're building. Any other questions?